probability of transitioning from one belief state to another belief state. So that is given by probability of B dash given my current belief B, comma A, right? Now, this can be written as the probability of seeing this observation given my A, comma B, okay, and the probability of the next belief given this observation, right? So now I can expand this further, okay? So this is basically the probability summation over O belonging to O, the probability of B dash given A, B, O, okay, this is fine. Now let's take the probability of the observation given AB, right? So now this is nothing but summation over all possible states, okay? Now the influence, like, which is basically what is the probability that I will make this observation given state is S dash and O, summation over all possible states, the transition from SA to S dash multiplied by B of S. Is that clear? So what is, okay, there are a few things here. So I'm interested in computing the probability of this observation, right? So how would this observation come from? So first, there is a probability distribution over the current states, okay? So then there is a probability distribution over moving from the current state to the next state, okay? So then you have the probability distribution over generating this observation given the next state, okay? And in fact, we have access to all these things, right? Like, so, well, we don't have access to a transition function. Well, we might, like, if you're learning, we could learn a bunch of these things, like, so, but the point is, like, so this is now at least defined in terms of things that exist with the existing MDP and POMDP, okay? Now, one thing that we haven't discussed is, like, what is this? Like, how am I going to update my belief, right? So given that my current belief is B, I see some observation. How am I going to update my belief? Like, so now this update is defined as, let me go to the next page, right? Maybe I need to copy this. Okay. Okay, so now this probability of B dash given A, B, O, right? Now, so this is going to be 1 if BOA is equal, I'll tell you what is BOA, it is 0 otherwise, okay? Now, this BOA of S dash tells me what is my updated belief for state S dash, okay? Now this is basically Z S dash AO summation over S belonging to S, T of SA S dash B of S divided by the probability of O given A comma B. Okay, you can see that the probability of, so this is just the interior of the sum, like, so you're normalizing it by using the sum. Okay, so now this tells you how is your belief changing after seeing the current state and observation. Is that clear? Okay, so yeah, any question? Okay, so I think now we have everything that is needed for an MDP, right? So now I can talk about like B functions and Q functions based on this belief state MDP. Yeah.
Can you explain again this BOA part?
Okay, so this is basically, you started with some, let's say that you took some action and you reach a state S dash. Okay, now B is basically the probability distribution over the entire state space, right? Like, so after taking action A and observing O, how is your belief distribution changing? So what is the new belief state? Okay, so the new belief state is given by a bunch of things, like my current belief, and where do I transition, and how is that resulting in the current observation. So this is my belief given the observation. Like on the other hand, like, so here for this particular thing, right? Like, so integrating over all the states like here. So that is what the denominator is. So essentially, like, I could just rewrite this as summation over S belonging to S dash, set of S dash A O, summation of S belonging to S, T of S A S dash B of S. So this just gives me a new distribution over the states. So this integrates this one-step knowledge that I got. So like, you are basically updating your probability distribution by taking into account that now you made action, like, which took you from S to S dash. Okay, so now, for example, like, if I have to talk about optimal value functions, right? Like, so for a Q function in this MDP can be defined as summation over S belonging to capital S, B of S, R of S, comma A. If you think about the Q function for the MDP, it is Q of S, comma A is equal to just R of S, comma A plus gamma times the value of the next state, right? So now we have to consider the belief state update. So this becomes, so R of S, comma A becomes summation over S, B of S, R of S, comma A plus gamma times, okay. Now we don't know which next state we are going to be, right? So we have to integrate over things like, so summation over O belonging to capital O, probability of O given AB, B star of BOA. So BOA will give you the next belief state. Is that clear? Now the pi star of B is given as argmax of A belonging to A, Q of B, comma A. Okay. So now you can actually extend different algorithms that we have seen so far to the POMDP setting. Like, so we are just going to do one example. So the example is, let's see how to do value iteration for POMDPs by using belief state MDPs. Okay. Now, if we just consider the original value iteration for MDPs, like it is the idea of improving the value of the state, right? Like, so V of T plus 1 of S is equal to max over A belonging to capital A, R of S, comma A plus gamma times summation over S dash belonging to S, T S A S dash VT of S dash. Right? Now, I can actually extend this to POMDP and have a POMDP value iteration. Okay. So now a POMDP value iteration is going to have VT plus 1 of the belief state B is equal to max over A, RB of B, comma A, so which is the modified reward function, which considers the belief state, okay, plus gamma times summation over B dash belonging to B, so all possible beliefs, TB of BA B dash, VT of B dash. Is that clear? So now we can rewrite this in terms of the origin. This is for the belief state MDP. Now I can rewrite this in terms of the POMDP notation and say that BT plus 1 of B is equal to max over A belonging to capital A. Okay. Summation over S belonging to capital S, B of S, R of S comma A, fine, plus gamma times summation over O belonging to capital O. Now we are in the POMDP space. The probability of O given A comma B, BT of BOA. Okay, where we already know what is the probability of O given AB. Like it's a summation over three probability, like three entities, right? So maybe, is that clear? Any question so far? Okay, yeah.
Not a question, but it's like a notation kind of seems kind of bit broken because the first equation, you are summing over B dash, but like the belief system is kind of continuous access space, right? So I mean continuous space. So
oh yeah.
I mean,
okay. Well, I think it's like I think when you are dealing with continuous things, like you'll do integrals instead of sums. Yeah, so my notations are a bit loose here. But there are, okay, so this is also, well, like the source for today's lecture, like which I'll put later, is like a 2000 or 2003 paper, like which has totally different notations, like, and I think the paper also talks about ways to come up with a bunch of fixed vectors to represent beliefs, like we are not getting into the details of that here. Okay, so this is about the formalism, right? Like, so now let's talk about like how to do these kind of things in practice. Okay, so which would take to your question. Can you repeat your question now?
history is like kind of hyperparameter.
Yeah. So is history a hyperparameter? Okay, so now in terms of like how to like approach partially observable situations, okay, so like more principled route is like what we have seen so far. Okay, so you design these belief state MDPs. Now I did not really talk about like how to learn these components, right? Like, so now you can have neural networks like learning the belief state or like learning the transition of the beliefs and so on, right? Like, so now often you will have these. Okay, so okay, I hope the screen doesn't go away. Okay, so the problem with belief states is like, so often you have this denominator. Okay, so the normalizing constant, which is actually very difficult to compute. Like sometimes it is intractable, like sometimes it is just computationally too expensive. Okay, so if you attempt to come up with a practical algorithm, like which is just based on this belief state MDP framework, it is going to be extremely slow. Like, so like and computationally very demanding. Okay, so this is one route. Okay, so of course, like you can explore more about this like by following up papers on the top of this. Okay, but there is also a more practical route which like people use in deep reinforcement learning to deal with POMDPs, like which is basically dealing with POMDPs using better state integrator functions like recurrent neural networks. Okay, now a naive way to take an MDP algorithm and just making it like work with POMDP settings is about like, is this like stacking the history, right? Like, so like, for example, in the case of DQN, like for Atari, right? So you are taking some action, but this input to the DQN was 4 time step frames. Like, so it was OT, OT minus 1, OT minus 2, OT minus 3. Okay, so you pass all these previous 4 observations and you have a network which is trying to predict the next action. Now, this was sufficient for simple Atari games, like where like, as I said, like you can get an idea of like where things are moving by just looking at the previous 4 or 5 frames. Okay, but this might not be sufficient for a lot of practical situations, like where you really need to model the entire history. So now, if you go by this approach, then yes, like your history is a hyperparameter, right? Like you decide whether you want to have 5 or 7. But there are a lot of other elegant ways of integrating information over time in deep learning. Okay, so like one standard architectural choice for doing this is recurrent neural network. So the basic idea here is, given my current observation, okay, I'm going to pass it to a neural network which is taking actions. Let's say could be a policy network, in which case it is taking action, or it could be a value function estimator, in which case it is giving you Q value or S value. It doesn't matter. Okay, so the idea is like the function approximator here. Like if you have a neural network function approximator, now this is the vanilla like multi-layer perceptron style neural network, right? Like, so now if you have some recurrence in these neural networks, okay, and this is going to integrate information from the past. Okay, so how is it doing? Like, so for example, like let's just assume a simple MLP function approximator. In this case, it is going to compute some hidden state, okay, which is some function of the current observation, okay, and you're going to take some action, which is a function of HT. Okay, now this function could be something like sigma of WOT plus B, and this function could be just VHT plus C. Okay, now the idea of adding a recurrence here is to keep track of the previous history. So how do I do that? Like I can do that by introducing an extra term here. Like so instead of having HT, which is just a function of OT, I can have HT, which is a function of OT and HT minus 1, and then take an action which is based on HT. Okay, now indirectly my action is taken, my action is taken based on HT, but HT is a function of HT minus 1, which is a function of HT minus 2, and so on, which means that I am kind of integrating the entire history, like of the trajectory up to this point, right? Like, so now like one implementation of this is just sigma of WOT plus, let's say, some P times HT minus 1 plus B. W and P are matrices, okay? And this is the same VHT plus C. Okay? Like one way to understand what a recurrent network is doing is like it takes O1 and it makes some action A1, okay? Then when it gets O2, it is not just constructing the state based on O2, like it is also taking the previous history into consideration, and it makes a prediction A2. Okay, so then O3, right? So now you can see that when the agent took action A3, it is actually a function of O1, O2, and O3. But it is a compact representation of O1 and O2 and O3, right? Like, so the H that you're seeing here is a compact representation of O1, O2, O3. So now, if you use a recurrent neural network with DQN, okay, so then you will get a recurrent DQN, which can actually start acting in partially observable environments. Similarly, you can take an actor critic, add a recurrent neural network as a function approximator. Now you have a recurrent actor critic architecture, like which could again handle with partial observability. Is that clear? So I think that concludes our discussion on partial observability. So any more questions? Yeah.
This is just a general question, like even though if you use LSTM, like if the text is long or like still it has some challenges, right? Like so when we take a real-time robot which generates 100K or like 1 million histories, so do you think this it is scalable to that extent, or like it has some
Okay. Okay, so that's a deep question. So the question is like, well, I think a plain way of putting the question is this the solution? This is not the solution, right? Like if this is a solution, we will discuss it in more detail. So of course, there are a lot of practical challenges in doing this. Like, so for example, like if your history is 1,000 time steps, like can I integrate all the information? Even though RNNs have the expressive power to integrate all the information, our current learning algorithms are not good enough to do this. Okay, so gradient descent is like not so great when it comes to things like this. Okay, so we cannot integrate all the information just because we are using an RNN. Okay, it is going to be better than not doing anything at all, but it is not going to be the best solution. Now you are talking about a continuing task, right? So in episodic tasks, maybe this is manageable. Like if your episode is 100 time steps or 1,000, even 1,000 times, or even 5,000 times, okay, it is still manageable with the current advances in like RNNs. But if you have a continuously acting robot where there is no notion of episodes, like it is a continuing task, then probably you could have 1,000,000 time steps behind you, so you cannot integrate everything. Right. So I think in those situations, like the fact that you cannot integrate everything with an RNN is kind of okay, because as long as you have memory about some recent past, you can act using that. So then you can think about some of the other recent advances in deep learning, right? Like, so you can use architectures like transformers, like so which can actually have attention over like a good amount of history, right? Like, so now you can combine these kind of, so the reason why I don't explore here further is like this is a reinforcement learning course, so we can actually construct a deep learning problem here and study it in more detail. Okay, so like we will just abstract it out. Any other question? Okay, so I think that concludes our discussion on partially observable situations and how to deal with partially observable situations. Okay, so now let's move to the second topic that I wanted to talk about today, so which is the idea of offline reinforcement learning. Okay, now so far, like almost all the algorithms that we have discussed are based on the principle of learning through interaction, right? Right now, even in learning through interaction, like so we discussed two broad classes of algorithms. Okay, so one is on policy and the other one was off policy. So in the case of on policy algorithms, like so your behavior policy and target policy are same. You are taking an action, you are learning immediately from the action, right? Now, like this is how a pure online oral algorithm would look like. So like you have a policy which takes an action and that gives you the state and reward. Okay, now after this one round of interaction, like you're going to update and get a pi k plus 1 and you go and interact again, right? So this is online oral. Now we have also done off policy oral, which is kind of in between online oral and offline oral. Okay, so why? Because in the case of off-policy oral algorithms like DQM, so you have the same interaction setup. Okay, so there's A and state and R. Okay. Now, based on this interaction, like you normally collect a buffer of data set D. Okay. And then you use this buffer to update your policy, and you go and interact in the world again. Right? So there is already some notion of learning from data here, because we are doing our updates based on the buffer, not from our interaction directly, right? So if you think about how we framed the deep queue network setup, like, so the agent will be acting, it will collect data, it will put the transitions in the buffer, and when we want to update the agent, like we were randomly sampling a mini batch from the buffer, and we were using that mini batch to update the agent, right? So now that is off policy RL. Now, what do I mean by offline RL? Right. So when I say offline RL, it means that there is some interaction with the world, okay, that happened with some policy beta. Okay. Sometimes we might know what the policy is, sometimes we might not know like what the policy was. Okay. Now, this policy need not even be an artificial intelligent agent. Okay, so it could be the human experts, like so humans interacting in the world, and like we are just recording all the interactions. Okay, now we are going to take this to construct a buffer of data set. Okay, now I'm going to use this buffer to learn the policy pipe. Is that clear? So once I learn the policy pi, I'm going to deploy the policy in the world. Okay. Now, there is a clear training phase here. This is the training time for your agent. And during the training time, there's no interaction with the world. The agent just learns from what is given to it, like the data set. Okay. Now this looks very similar to supervised learning, right? Like so in supervised learning, let's say if you want to do image classification, you don't learn by asking the model to go and predict after deployment, right? Like so you collect millions and millions of examples of classifications, and you train the best possible system, and then just go and deploy the system, right? Now, offline RL is very similar to supervised learning in that sense. Okay, however, well, there is a big difference between the two. We are going to talk about it, but in terms of the setup, it is very similar to the supervised RL. Okay, is that clear? Now, the first question. So, why should I do something like offline RL? Yeah.
It's less costly. You could train a robot, for example, in like a virtual environment, and then deploy it in real life.
Okay. So now, offline RL is not same as training a robot in a simulator. Okay, I'll come to that. Offline RL is about learning from a data set. So in learning with the simulator, you're interacting with the simulator. Like so, what I talk about here is like there's no interaction. So why would one do this? Yeah.
To make the agent more robust, where there is mistake can be very costly.
So whenever mistakes are costly, like so, you don't want to learn through interaction and have very costly mistakes. So typically safe reinforcement learning. Okay, yeah.
You might want to use offline RL as a way of giving a head start for an online RL.
Okay, so that is another really good application. So Just give me 1 second.
So like if the data is always available, so you might as well not
Yeah,
start from
that's actually another good application. So like you can consider offline oral as a pre-training strategy for online oral. Okay. Yeah.
Interaction is like real world interaction is expensive, and collecting the data is relatively cheap.
Yes, so interactions are expensive and data is cheap. So in some sense, like, can we say data efficiency? Like, if the data is very expensive, why do you throw it away, right? Like, so you should extract as much knowledge from the data as possible, as possible. Okay, I think these are good reasons, right? Like, so for example, there are a lot of applications where directly doing reinforcement learning is either not possible or simply not allowed. Okay, so I think one of the examples that I gave last week is like the agent navigating in Mars, right? Like, so the Mars navigation robot, like, so there is no way like NASA is going to let you do learning through interactions with that agent, right? Like, it's a costly affair. Like, so like you can only collect data, like, and do whatever the best learning that you can do in the earth. And then when we send the next robot, like, so you can have a better policy for that robot to interact, right? Like, so that is like one very good example. And there are also a lot of examples in healthcare. So for example, let's say you want to take decisions about treatments. Now, first of all, in sensitive applications like healthcare, doctors are not comfortable even using the best possible, like, already learned system. Okay, so now if you say the doctor, okay, so I'm going to install the system for you to take actions, like take decisions in your treatments, and it is going to learn through interaction, right? Like, so now no doctor is going to allow you to install such a system. Like, so it is just not allowed because of the regulatory reasons, and also for all other obvious reasons that, like, you cannot learn through interaction there. Like, so you can only learn by looking at how the doctor behaves and come up with the best possible expert agent, then demonstrate to the doctor, see, like, so this is actually doing things almost like you, like, or sometimes better than you, and now we are going to deploy the system, right? And maybe another example that I could give is like goal-directed dialogue systems. Like, so let's say we are interested in coming up with chatbots, like not for chit chat, like, but for like for a purpose, right? Like, so like you might have interacted with like reservation systems, like, which are chatbots, like, so where the goal is to make a reservation. The system is going to ask you a series of questions to achieve the task, right? Like, so now again, if the company is going to deploy a reinforcement learning agent, which is learning to achieve these goals, like, so they're going to lose all the customers. Like, so like customers don't want to talk to a learning agent. They want to talk to a learned agent, right? Like, so this is another example, like, where you can take hundreds of thousands of historical dialogues between a real human who is helping someone with the reservation system and learn a policy which would like do the same task, similar or in a similar or better way. Okay, and I think somebody also talked about the robots. Like, so like in the case of robots, like interactions are very costly, and it is also extremely risky to do adventurous things with robots. Like, sometimes a robot would cost multi-million-dollars, right? So like imagine an academic lab buying $1 million robot and the grad student breaking it in a week. So, but these robots sometimes cannot be fixed. So sometimes the fix costs millions of dollars. Okay, so now in those situations, especially, like, so you want to be as safe as possible. Now, it is not just about safety; it is also about the speed. The speed of interaction is extremely low, is extremely low in like real physical robots. With a simulator, you can do hundreds of things in parallel, right? Like, you can have like 100 agents acting in parallel in the simulator. But in real world, you have only one robot it is going to do moves like very slow. Like now, if you want to do million episodes with like a slowly moving robot, it is going to take you a lot of time. So in those situations, like you want to make use of everything that you have done so far. Okay, so in some sense, like it would be nice if we can have multitasking ability for these agents, right? Like, so if I can use the historical data, not just for example, grabbing the bottle task. Let's say in the past, I have worked on tasks like picking up the telephone or turning off the switch. Okay. Now, if I can use some part of the skills learned from those tasks to the new task, then like it is a good thing to do, right? Like, so now if I can collect data from all these different tasks and learn a generic policy, like that is going to be extremely data efficient. So that was a question.
Yes. Could you clarify about the robot example? Because you mentioned earlier that this is not an example of offline or
okay. So okay, so maybe I'll talk about that. Like, so this, like, I think your point was to train the robot in simulator and then deploying, right? Like, so that in the real world robot. So that is one way. That is another way to handle this problem of like speed limitations and like interactions being costly. So if interactions are costly, okay, here's the thing. You can actually do all these things with another technique than offline oral, okay? So which is the idea of sim to real. Okay, so whenever you are in situations where interaction is costly or interaction is not safe, okay, or interaction is just taking a lot of time, like the robot example, right? Like, so what you can do is you can build a simulator for the environment. Okay, it's a virtual simulator. Like, for example, like in the case of self-driving cars, like there are simulators like Carla, like, so like you can go check. So Carla is like a simulator which gives you a good, real, almost realistic environment for driving. Okay, so now it is actually very risky to put a real car in the road to learn, but you can put a car into the simulator to learn. Now this car can crash 100 times or like 1,000 times or 1,000,000 times if it wants, and like there's no danger. Like, and it could also learn faster because I can put the simulator in parallel, like 1,000 simulators in parallel and 1,000 agents acting in these simulators, right? Like, so like I can do all these things in simulator and take the policy and extend it to the real world. Okay, so the basic idea in sim to real is a bit different from these pictures. Like, so in the case of sim to real, like you have a simulator and the policy is updated using the simulator. Okay, so now here you can actually use online RL or offline RL, like whatever you want to use. But once the simulation phase is over, you're going to take the final policy pi and put this policy to act in the real world. This is real world. Okay, like for example, like for a robotic arm, like you can have a simulator where the arm actually learns how to pick the bottle 1,000,000 times. Okay, now you cannot do that physically, like probably it is going to take you a few months. Okay, so but you can do this 1,000,000 times in a couple of hours and then take that policy and put it in the real world. However, I think probably when I teach the advanced course, like, so we will talk more about sim to real. However, like it is not like the most like easy. It's not a very easy solution. Okay, it looks from the way I explain sim to real, it looks like you can learn everything in simulator and then like come up with a good policy. But there are a lot of challenges, research challenges there. Like, so first of all, who gives me the simulator? Like, so like it requires a huge engineering effort to come up with a simulator for a problem. Okay, so like most often you have to like do a lot of physics modeling, and like this is very complicated. And sometimes if you can put so much effort into the intricacies of the world, you could very well learn like a heuristic to solve the problem. Okay, so sometimes it is possible, sometimes it is very difficult, and there's going to be a lot of approximation errors in the simulator, which is going to be a problem, because now you're learning a policy for this approximate world. When you go to the real world, the distribution of the states might change. So you face out of distribution issues, and like it is not very clear how to act, right? Like, so now there are other issues, like, so for example, like, can you have the same state simulator? For a lot of problems, you cannot. So you're going to have an approximate state. Now, how do I transfer my policy from this approximate state to the actual state, right? So like transferring from simulation to real is a big challenge. Like, so we don't have, well, we have made a lot of progress, but like, so we don't have the solution which works out of the box, okay? Now, the fact that reinforcement learning community is using sim to real is one of the motivations for offline oral. Like, so like we are doing sim to real because it is easier than doing offline reinforcement learning. Okay, so we're going to talk about the challenges in offline oral. But one thing that I want to highlight is like you take any other domains like language, natural language processing, or computer vision. So learning from data is the most prevalent paradigm there. Like, so you learn from lots and lots of data, you have the best possible classifier, right? Like, so now that is not possible, or that it is just very difficult to do, like learning from data, like for reinforcement learning, because the paradigm itself is fundamentally an interaction paradigm. So we wanted to fake interactions, like, so that's what sim to real is doing, right? Like, so like it's better than like not having any interactions at all. Okay, yeah.
Just a quick question, like I need your opinion on like when I speak with autonomous vehicle students, like mostly they use a traditional robotics stuff, and when I speak with my internship company where they have robotics team, so they have autonomous bots, but everything is built on traditional line following, path following.
Okay.
So like, what do you think, since you work in reinforcement learning as a future in terms of cross section of reinforcement learning and robotics?
Okay, so well, I think there are probably a couple of robotics course at Poly as well, like, and there's also like a new robotics course coming up at UDM by the new prof. So one thing, like probably like I want to highlight is robotics is not, well, maybe, well, this is like we are putting the video on YouTube and like maybe it will be controversial, but robotics is, but I think it's a fact that robotics is not as advanced as like other fields like computer vision or natural language processing. Okay, so like we still use a lot of traditional non-learning, like, but more planning techniques in robotics. It is simply because learning with physical robots is extremely hard, but sim to real has made it possible. Like, so now there is a lot of work on like learning from simulator and bringing it to the real world robots. But even now, like a lot of robotics applications, like there is not a lot of learning involved. Like, so well, like I think people coming up with new startups might say that like they have a reinforcement learning agent behind their robot, but probably it's just a sophisticated planning algorithm. Okay. Similarly, if you talk to a lot of autonomous driving startups, like, so they are still hesitating to use reinforcement learning. Like, so like even though we talk about driving as an application for reinforcement learning, they mostly use traditional methods, like, so which are like more safer. Okay. However, like that is also one of the motivations for these kind of like offline reinforcement learning methods. Like, so if we can develop better offline reinforcement learning methods, then we should be able to like one day push RL to these kind of applications. Okay, so I think I gave a lot of motivation for doing offline reinforcement learning. So now, well, I don't want to start and finish it in a few minutes. So let's take a break. So we will start talking about some methods at level 11:30. Like we can do 11:30. Like I have short content. Okay.